Okay, we have a fairly classic calorimetry problem here. And what we have is a block of copper at a certain temperature is dropped into an aluminum calorimeter cup that's containing some water. So think about like we have this aluminum calorimeter cup, and there's some amount of water inside the cup, and then there's a block of copper. This is water. So those are our three materials there. The copper is initially at 300 degrees Celsius, and we're told that the aluminum and the water are initially at 12 degrees Celsius. Put them all together, we're going to assume the calorimeter doesn't exchange energy with the environment at all, so it's a closed system, and that our energy is conserved there. So cool. If we were meeting in class, this is the kind of lab that you would do at least once, and many of you have done this already in chemistry, I know. So, a way to think about this, if our energy is conserved here, we make that assumption that the basically a way to think about that is the Q lost plus Q gained equals zero, right? So that we have a conservation of energy within our system. Now, what is losing? And that's the copper, right? The copper is going to cool down. So you can think that there's energy transfer from the copper. And we can write that as M copper, C copper, delta T of the copper. The gained, the water and aluminum are both going to go from a cooler to warmer temperature. So mass of water, C water, delta T water, mass of aluminum, C aluminum, delta T of aluminum. So one of the things that I know here is that the delta T of copper is going to be equal, I can write that as the final temperature of the system minus the initial temperature of the copper. And the delta T of water is equal to the delta T of aluminum. They're both together, they change temperature together, they're initially together. And I can express that as the common final temperature minus the initial temperature of water and aluminum. Okay, so we have to, kind of figure out notation that makes sense for everything. That's important in a problem like this. So I'm going to do this totally symbolically, and you can sub in numbers later. I'm doing it symbolically because it shows a little bit more clearly what the overall path is. And then remember, symbolic solutions are solutions that you can code into a computer and allow the user to solve for all kinds of different cases, right? Okay, so now we can set this up using this general idea up here of looking at our energy lost and energy gained. So solving for T final here, I'm just going to use this approach above Q lost and Q gained here. So my Q lost, MC, looking at my copper, T final minus T initial for copper is equal to my Q gained. Actually, I think I'll sum those here. And now I'm looking at the water and aluminum. T final minus T initial, water and aluminum, equal to 0. Okay, and now I need to solve for T final. And if I do that, I get that T final is equal to T initial of water and aluminum now plus T initial of copper times MC for copper. And here are all three of my materials. In the denominator. So that's my symbolic solution there. If you end up substituting in all these numeric values, what you'll get, if everything's subbed in correctly, you should get something around 20.2 degrees Celsius for your numeric answer here. And remember, when you get this final answer, if you're doing a numeric problem like this, you're going to expect a temperature that's in between the two temperatures of the two in the beginning, right? So here we were given this block of copper at 300 degrees Celsius, and we were given the water at 12 degrees Celsius. So it does make sense to me that the equilibrium temperature of the system as a whole would be somewhere between those two values.